Let us talk about estimation. What is estimation? Estimation is a statistical technique of inferring the parameter of the population, which is fixed and unknown, from the statistical summary of the sample, which is the sample statistic. The population parameter can be mean, proportion, or variance. We have two types of estimations: point estimation, which is a single value estimate of the population parameter, and the interval estimation, which is in addition to point estimate provides an interval around the point estimate which is likely to cover the population parameter. Let's understand what is point estimation and what is the limitation and how central limit theorem helps us. The statistical technique for a single point estimate of the population parameter is called point estimation, and the estimate is called as the point estimate. The central limit theorem states that the mean of the sampling distribution of a sample statistic is the best estimate of the corresponding population parameter. Now, the sample statistic that we derive from our sample has originated from this hypothetical sampling distribution, where the most likely value or the expected value of the sampling distribution is the true population parameter. That's what our central limit theorem tells us. So when we have the sampling based sample statistic available, it is the best and the most probable population parameter estimate. So we use the sample mean or the sample statistic as the estimate of the population parameter. Now, the confidence that we have in this point estimate is not so great because of the two inherent limitations. One, the sampling error and the sampling bias. Sampling error and sampling bias together result in the difference between the actual population parameter and the estimated population parameter, the point estimate. It is called as the error in the estimate. Let us look at addressing the sampling error and the sampling bias. The sampling bias, which is a systemic over and underestimation of the parameter, the population parameter, it can be minimized through appropriate data collection methodology, research design, and the measurements used in the study. We can reasonably minimize the sampling bias by using well-established good practices and conventions. Sampling error is inherent in the sampling process. We can reduce it by increasing the sample size. We can make it zero by making the sample size equal to the population size, which is practically and typically infeasible. Also, we ensure randomness in the sampling process, or we guarantee that there are no biases because of the sampling process itself. And oftentimes, when we still are not confident, we replicate the study. Now, the sampling error is inherent. We cannot do away with it. So to overcome the inherent sampling error, we enhance the point estimate by bringing an interval around the point estimate within which we expect to capture the population parameter with a certain degree of confidence. The degree of confidence is also called as confidence level, and the width of the interval is also called as the confidence interval. Before we get into the formal definition and quantification of the confidence level and confidence interval, let us review the center limit theorem in the context of the interval estimation. In real world, we never actually observe the sampling distribution. But yes, it is useful to always think of a point estimate as coming from such a hypothetical distribution. So, the guarantee or the confidence in the point estimate comes from the fact that the sample statistic has originated from the underlying sampling distribution, which is a hypothetical sampling distribution, which is always a normal distribution. Understanding the sampling distribution help us characterize and make sense of the point estimates that we do observe. So the sample statistic is the most plausible estimate of population parameter. We build the interval around this point estimate. The interval is determined by the standard error. From center limit theorem, we know the standard error of the sampling distribution of the sample statistic is sigma by root n, where sigma is the population standard deviation and n is the sample size. With this understanding, let's define the confidence level and confidence interval. So confidence interval is the range around a point estimate that likely contains the true population parameter, and the confidence level is the width of the confidence interval with a certain degree of confidence associated with it. So how do we build it? Let us construct an infinite confidence interval. When you say that a particular population parameter is between minus infinity and plus infinity, that's a infinite confidence interval, you will have 100% confidence in it that you have captured the true population parameter. But such an interval is practically useless. We need to have something which is workable, the deviation that is useful and meaningful. On the other hand, extreme, we can construct a confidence interval with zero width. It will reduce down to your point estimate. But the confidence in the point estimate as the true population parameter is very, very minuscule or zero. So statisticians have come up with something in between this zero confidence level and 100% confidence level by accepting a convention of 95% confidence level when constructing the confidence intervals, so that the interval around the point estimate captures the true population parameter with a 95% chance. So let's see what does it mean visually. So once we have estimated the point estimate, we build a confidence level around it which will follow a normal distribution, and the degree of confidence is indicated by the area under this normal curve. The confidence level's complement is called as significance level, and it is equally split on the either side of this interval as the interval is symmetric. Sometimes we may have a asymmetric interval when we know that the value is greater than a certain expectation. So the interval around the point estimate is the confidence interval, and the area captured by the normal curve within this interval band, confidence interval band, is the confidence level. Now let us apply it to the context of a mean. The point estimate of the population mean mu is the sample mean x bar. Now we can build the confidence interval around it, where we will use the standard error of the sampling distribution of the mean, which is given by sigma by root n. So the interval estimated 95% confidence level is the x bar, that's the point estimate, plus or minus the z value corresponding to the 95% confidence level, times sigma by root n. The z value is this threshold is plus and minus 1.96, and we can determine the respective z values for different confidence levels. We can choose our own confidence level, but in the academic world and in the reporting conventions, we typically follow 95% confidence level. This quantity z times sigma by root n is called as the margin of error. So E equals z sigma by root n. So we have these four quantities related with each other with this formula. If we are given any three, we can determine the fourth. So we can repurpose this E is equal to z sigma by root n to arrive at a formula for n, which will be n equal to z sigma by E whole square. Now for a given confidence level and a given confidence width or the confidence interval and a given population standard deviation, we can determine the right sample size. Similarly, we can apply this to the proportion also. So population proportion P is the sample proportion P hat, the estimated value of the population parameter. The standard error of the sampling distribution of proportion is given by root of PQ by N. So the confidence interval would be given by point estimate of P plus minus Z times root of PQ by N. And the width of the confidence interval is of course Z times root PQ by N. So we can determine N will be equal to Z by E whole square times PQ, where P and Q are related by the relation Q is equal to 1 minus P.